Hello everyone, this is the first author Xin Wang. In this presentation, I'm going to talk about using self-supervised frontend for speech anti-spoofing. The task is to build a countermeasure that discriminates the real human speech from the synthesized speech. So in this talk, we refer to the real human speech as bona fide, while the synthesized speech as spoofed one. Such a countermeasure can be used to protect the ASV system. It can also be used to detect the fake voice in phone scam or the deepfake video. Many of us use machine learning techniques to build the countermeasure. We will use a training set to train the model, and we will use a test set to measure the model performance. For anti-spoofing, there are many corpora that provide the training and test sets. For example, the ASVspoof challenge databases and other Mandarin databases. It's normal to have unseen speakers and unseen spoofing methods in the test set so that the performance we measured on the test set can somehow reflect the real performance of the countermeasure in real scenarios. By doing so, we really hope that countermeasure can work in the real scenarios to detect all types of spoofed data regardless of the languages, the speakers, the compression methods, or even spoofing methods. Unfortunately, a few studies have shown that the countermeasure training in such a way cannot generalize well. For example, if we train the countermeasure on the 2019 ASVspoof training set, its performance on the test set of the same database would be, for example, less than 8%. But its performance on the 2015 test set would be higher than 20%. The degradations across the different test sets indicate the countermeasure is not generalizable enough. So the question is, how can we improve? One obvious way is to include more diverse training data to train the countermeasure. But in this study, we will show how can we use self-supervised model in order to implicitly use information extracted from a huge amount of training data without, say, time-consuming training process. So in this study, we want to build a countermeasure that can generalize to multiple test sets. And the method is to use the self-supervised speech model as a feature extractor. In speaker verification and language identification, the SS model has been used as a feature extraction. So the motivation here is the same. Since the SS model was pre-trained on a huge amount of speech data, we wish that it can extract more robust features from the input waveform. Now let's look at the implementation. First, let me introduce a baseline model that uses a conventional front-end. So in this case, we need the front-end to transform the input waveform X into a sequence of acoustic features A here. For example, if we use linear frequency capstone coefficients, we need STFT and DCT to transform the input into the output. By using the SSO-based frontend, it's straightforward. We just replace the frontend, the DSP-based frontend, with the SSO model. This model also converts the input waveform into a sequence of acoustic features, but in this case, we're using neural networks. For example, if we use WAG 2.2, we will use CN and transformer to process input and get the output sequence of acoustic features. So as you can see, it's straightforward to plug the SSO model into the countermeasure. One advantage of using SSO model is that because the SSO model was pre-trained on a huge amount of waveforms covering different languages, speakers, and the room acoustics, we hope they can extract more robust features. Another advantage is that many pre-trained SSO models are provided on GitHub, for example. We can directly download them and use them in the countermeasure. So we don't need to do the self-supervised learning by ourselves. But of course, there are a few questions we need to answer when we build such a countermeasure. For example, whether we should fine-tune the SSO model on the anti-spoofing database, and what kind of backend should we use to process the output from the SSO model. So these are the questions I would like to answer in this presentation. For the experiments, we use the logic axis training set from the ASVspoof 2019, and we use multiple test sets from the ASVspoof challenge. Although the test sets are all from the ASVspoof challenge, but they have different attributes, so they are quite diverse. For example, in this deepfake evaluation set, you can see the source data are not from VCTK, but from different databases. Also, the languages includes not only English, but also other languages. The quality is also diverse. For example, some of them are processed by the codec or compression methods, while some of them are clean as the training set. Furthermore, the spoofing methods are different in these test sets, and there are many unseen methods not covered by the training set. So we think this design of training and test sets can be more useful to measure the countermeasure performance in real scenario. In terms of the model configurations, the baseline was from our previous study. So the backend consists of LightCN followed by LSTM, global average pooling, and fully connected layers. For experimental models using self-supervised frontend, we prepared 3 variants. So the first one uses exactly the same backend architecture as a baseline. So the other 2 gradually remove the LightCN and the LSTM layers. In terms of the front end, the baseline uses the LFCC. The experimental models I will explain in this presentation only use the Wave2X 2.2 trained on multilingual database. The front end can be either fixed or further fine-tuned on the training set we used for the countermeasure. So notice that we include one fully connected layers after the self-supervised front end in order to compress the dimension of the front-end features. The results are plotted in this bar chart. Baseline system on the right-hand side, 3 systems in the middle, they use the fixed pre-trained SSO front-end. The 3 on the right-hand side further fine-tune the front-end. For each system, we have 4 bars. They indicate the system performance on the 4 test sets. The first thing I'd like to highlight from the results is the baseline. We can see the baseline performance on the 2019 test set was quite good. The equal error rate was around 3%. But if we use the same system to evaluate the 2015 evaluation set, the equal error rate goes to around 30%. Also, the ER on the 2021 test set were also higher than 20%. So we can see the degradation of the model performance across different test sets. And this is consistent with the findings from previous studies. However, if we use pre-trained SSO model, we can see the ER dropped, improved for all the 3 additional test sets. Furthermore, if we fine-tune the SSO model, the performance would be better. Especially on the 2015 test set, we can see the equal rate was less than 1%. So this should be the expected performance. By comparing the results of other systems using SSO frontend, we can notice it would be useful to fine-tune the SSO frontend for the countermeasure. If we don't do that, then we need a deep backend in order to increase or improve the performance of countermeasure. However, if we do the fine-tuning, the choice of frontend seems to be less important, at least from the results of our study. So a quick summary of what we have found in this study. Yes, the countermeasure using SSO frontend seems to be more generalizable to different test sets. And our study recommends using a large SSO model pre-trained on diverse data, and also it's better to fine-tune the SSO model front-end for the countermeasure. However, we also like to point out even the best model from our study is not sufficiently generalizable. So if we use the same model, for example, on Mandarin or Japanese data, we still get ER higher than 10%. So there is still room for improvement. Finally, I'd like to mention that in the paper, we have additional findings try to explain why the SSO front-end was better than the conventional front-end, and also the performance of a countermeasure on different types of spoofing methods. Furthermore, there are findings which can be useful related to this topic from other studies. For example, it was found that data augmentation is still useful even if we use a SSO frontend. Also, the backend used in this study was not the best choice. So in the next presentation, I think Hemalata from Eurocom will explain how can we use a more advanced backend to further boost the performance of the countermeasure. That's all from this presentation. You can find the codes and pre-trained models on our GitHub. Thank you.